This is section 5.5, talking about the inverse specifically of exponential functions. So we're really looking at putting together some of the things that we've been looking at so far in this unit. Exponential functions, and now inverses of them. So we already know that if we can create a table of values for a function like this exponential function, as long as it's one-to-one, we'll be able to very quickly just flip the x and y and have a table of values for the inverse. So let's work on that. If I'm looking at 2 to the x power, 2 to the negative second, that's 1 over 2 squared, or 1/4. 2 to the negative first would be 1 over 2 to the first. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8. First of all, is this one-to-one? Well, as I look over here, all of my outputs are unique, right? There's no repeats, meaning I don't have two of the same output that came from different inputs. So I'm going to say yes, this does seem to be one-to-one, and therefore yes, it has an inverse. Let's switch our x's and y's to get a table of values for the inverse. So we're going to go ahead now that we've got this, and we're going to graph both the original function, the 2 to the x, and now this new inverse function together on the same graph. Oh, let's see. Let's do the original function. I'll do that one in green. We already know it's going to be exponential growth, so we have a pretty good idea of what it's going to look like, but let's just plot the points and we'll get a quick graph here. And there we go. All right, the inverse function, we now have some points to graph. I'm going to do that one in pink. So let's see, 1/4 2 would be about there. Oh, sorry, that was 1/4 negative 2. Ignore that point. 1/4 negative 2 down here. 1/2 negative 1. 1 0. 2 1. 4 2. And 8 3. So I can kind of see that graph going up fairly slowly, but going up. And then over here, it seems to be approaching the y-axis. That makes sense, since the original function was approaching the x-axis. The inverse would approach the y-axis. Notice that if I were to add in, just sort of as a dotted reference line, that diagonal, y equals x, we can see that reflection across the y equals x line, which is typical for our inverse functions. Right. So we have a new type of function, something that we haven't seen before. We've never seen a function with a vertical asymptote, at least not yet in this class. So this is brand new. And when we get something brand new, typically what we want to do is give it a name. And the first person who worked with this decided to call this new function the logarithm function. So if my original function was 2 to the x, that was an exponential function with a base of 2. My new function is the inverse function, and that's going to be given the name the logarithm, base 2 of x. Sorry, froze for a second there. So I've got 2 to the x, my original function, and then the inverse is the logarithm, base 2. Notice that the base for the exponential and the base for the logarithm are the same. All right, your notation is given here at the bottom of the page as well. I'd like to write out a few statements using logarithm notation. And we can use our tables from the previous page a little bit to help, but I think we'll be okay here. Notice that when I say that my original function, 2 to the third power equals 8, the output for the exponential becomes the input for the log. The log base 2 of 8 is equal to 3, right? Input and output trade places. So if I do f of 2, 2 to the second power equals 4. And now if I write my inverse function, my output was 4, that becomes my new input into the log base 2 function. And that equals the original input, which was 2. A couple more. F of 1. 2 to the first power equals 2. So f inverse of 2, or in other words, the log base 2 of 2, would equal that 1. And one last one, f of 0. 2 to the 0 equals 1. So when I go to my inverse function, my new input is what my old output was, f inverse of 1, or the log base 2 of 1, would equal that 0. Okay? And those I just kind of did by rote, just switching the inputs and outputs. But what I'd like you to notice now is the pattern that we've established. The base is always 2, right? That became the base when the original exponential function had base 2. The log base, actually, let's go all the way back up even to this one. The log base 2 of 8 is equal to 3. Did you notice that what I'm really looking for is the exponent, or the power, that I would have to put on that base of 2 to get an answer of 8? Right? 2 to the third power gives us 8. Continues down here. 2 to the second power to get the 4. 2 to the first power to get the 2. 2 to the 0 power to get the 1. So when we're finding a logarithm, what we're really saying is, hey, I'm telling you what the base is. You tell me what exponent I would need to come up with that answer. Let's try one more. This time my my original function g of x is 5 to the x. And so right away I definitely know that the inverse function, g inverse of x, is going to be the logarithm base 5 of x. An exponential function always has a logarithm function with the same base as its inverse. I could make a table of values for g and g inverse. And I'm going to make a relatively small one. Let's just do a -1, 0, 1, 2, and 3. 5 to the negative first would be 1 over 5 to the first. 5 to the 0 is 1. 5 to the first is 5. 5 squared is 25. And 5 cubed is 125. All right, let's make a table of values for the inverse. The logarithm base 5 of x. So I'm going to switch my x's and y's. And so what I'm now saying here, if I rewrite in that logarithm notation, is when I plug in an x of 1/5, The log base 5 of 1/5 is equal to -1. And the log base 5 of 1 is equal to 0. The log base 5 of 5 equals 1. The log base 5 of 25 equals 2. And the log base 5 of 125 equals 3. That was just by flipping the table and plugging in my values. Now let's think about it in terms of what it's really telling us, right? The base is 5. What power do we need to get to the 125? We need a third power. With a base of 5, what power do we need to get to 25? We need a second power, right? And so on. From a base of 5, we need a first power to get 5, a 0 power to get 1, and a negative first power to get 1/5. So when you're calculating a logarithm, what you're really doing is figuring out the exponent that you need to put on the base to get the result you need. All right. Let's go ahead and just real quick draw those two functions again, g and g inverse, on the same axes. I've got my points over here. I'm just going from this. So I'm going to once again start with my exponential function in green, and I'm going to graph those points. -1 1/5, 0 1, 1 5, and then it gets big really, really fast, right? The 225 won't even fit on the graph. But I kind of know this is just going to keep on getting bigger and bigger, and this side is going to keep on staying close to the x-axis. So because of what I know about exponential functions, I can graph that pretty well, even with only 3 points. We'll have some of the same issues with the inverse function, the log base 5 of x. I'm going to take as many of these points as I can, and I'll graph that in pink. So starting with 1/5, -1. 1 0, and 5 1. And the next point has an x value of 25, and I don't have that on my graph. So I'm going to say, well, that would keep on getting bigger slowly, and that's going to come really close, but not go past the y-axis. I know that based on what I already drew, and also on imagining that mirror line, that it's going to have to look like that. All right, I jumped the gun just a little bit. I said write at least 3 equivalent pairs. We kind of already did that because we've got our equivalent pairs here. So I might just steal a couple of them. Oh, let's see. Let's start with this one. 5 to the first power equals 5. The log base 5 of 5 equals 1. Notice they both say when the base is 1, excuse me, let me try that again. They both say when the base is 5, it takes an exponent of 1 to give the result of 5. We'll do another one. Five squared is 25, and the log base 5 of 25 is 2. Let's write both of those out. Once again, those are saying the same thing. With a base of 5, it takes an exponent of 2 to give a result of 25. And I'll grab one more. Let's do this last one. Five to the third equals 125. And the log base 5 of 125 is equal to 3. Now once again, these are really saying the same thing. The base is 5. It takes a third power to give 125. So the statements are really equivalent. They're just sort of stated in a different order, if that makes sense. All right, I'd like to work a little bit more with graphs of these logarithm functions. And I want to start by just taking a look at the first ones we already graphed. I've just regraphed them here for your convenience. But this is the first graph we graphed, 2 to the x, and its inverse function, the logarithm base 2 of x. The x-intercept for this, well, there are none, right? This never crosses the x-axis. And the y-intercept right here is 0, 1. How does that compare to the inverse function, the logarithm base 2 of x? Well, my x-intercept crosses the x-axis right there at 1, 0. And this graph never crosses the y-axis. It gets really close, but it doesn't touch it, doesn't cross it. So notice how we're seeing that relationship between x and y for inverse functions again, right? The x-intercept and the y-intercept, well, there aren't any. No x-intercepts for the function, no y-intercepts for the inverse. The x-intercept and the y-intercept here just show that reversal of x and y. So very typical of inverses. Right? The next thing we want to talk about are the asymptotes. We've already been talking a bit about the asymptotes of a exponential function. Remember that this approaches but doesn't cross the x-axis. Right? So the negative x-axis is a horizontal asymptote. On the inverse function, the logarithm function, this time it's the vertical, right? The function comes really close to that vertical line of the y-axis, comes close but doesn't touch or cross. So the negative y-axis is a vertical asymptote. Again, you see that reversal of x and y in the inverse functions. All right, as far as the end behavior, let's see. This one, on the left, we approach 0. Y equals 0. And then we go up to the right. This one's kind of interesting because the end behavior actually ends on this vertical asymptote. You can't go further to the left than x equals 0, right? It just doesn't exist. So I'm going to say on the left, we approach the vertical line, x equals 0. And it still goes up to the right. Okay, but once again, notice that xy swap here. All right, domain and range. The domain, we've already said, is negative infinity to infinity for all of our exponential functions. And notice that my range here, the smallest y value is almost 0, but not quite. So parentheses with the 0, and then it goes up to positive infinity. With the logarithm function, for the first time, we are seeing a function that does not have a domain of negative infinity to infinity. As we just mentioned, there are no values left of x equals 0. So almost x equals 0 is the smallest x value on that graph. And then we go out to the right to positive infinity. The range goes down to negative infinity on this side, and although it goes up slowly, it does keep going up. So it does go up to positive infinity. And once again, we've swapped here, right? The domain for the function is the range for the inverse, and the domain for the inverse is the range for the function. That same xy swap here. And that's what I mean by seeing the concepts of inverse functions illustrated here. All right, we're going to use that logarithm graph with the vertical asymptote on the x-axis rather, as our parent function. So we're thinking of the parent function like this. And we can then shift that in order to get different versions of the log graphs. Notice that the two things that are probably most easy to shift are the vertical asymptote and secondly, I'm going to say that x-intercept 1, 0. We'll shift that one as well to our new graph. All right, let's just take a look at how our shifts, which are now pretty familiar to us, are going to look in the case of the logarithm graphs. So if I have a multiplier of a on my function, for a logarithm graph, that's just going to be a times the log base b of x. I just use the b here to avoid saying, hey, it's base 2 or base 5 or whatever. It could be any base. We know that that's either a vertical stretch if a is bigger than 1, or a vertical shrink or compression if a is smaller than 1. If I have a negative leading coefficient, so I would have negative log base b of x. Again, from our past experience, we know that just reflects our graph across the x-axis. There are our two horizontal shifts, right? If I replace the x with x plus h, so I would have the logarithm base b of x plus h. Our graph shifts to the left, h units. And if I replace the x with x minus h, our graph shifts to the right, h units. And then finally the vertical shifts. If I take my logarithm and add some value k to it, our graph should go up k units. And if I subtract the value k, I will go down k units. Okay. None of that should surprise you at this stage, at least I hope not, because of the same shifts we've seen already 3 or 4 different times, right? All right, let's see how they look on a logarithm graph. All right, so I want the log base 2 of x plus 4. And I'm going to say as far as the transformations, we would have a vertical stretch, and we'd be going left 4. All right, I'd like to graph this right away, and then we'll talk about the rest of it. Since I'm going left 4, I'm going to say my vertical asymptote, which was on the y-axis, moves left 4. And now it's on the line x equals negative 4. My y-intercept, my x-intercept, which was at 1, 0, also moves left 4. So now it's over here at negative 3. And once I've moved those two things, the vertical asymptote and the x-intercept, I'm just going to sketch. I know I have to go down and approach that vertical asymptote. And then I go up kind of slowly on the other side. And that's as accurate as I'm looking for without using technology. All right, the domain here. Well, let's see. The x values don't start until just after negative 4. So my domain starts at negative 4 with a parenthesis and goes out to infinity. My range goes down to negative infinity and up to positive infinity. All right, try one more. This one is a slightly different logarithm. I haven't talked about it yet, but we're going to go ahead and do that right now. That ln stands for a natural logarithm. And that is actually the inverse function for e to the x. So if I wanted to, I could write that as minus the logarithm base e, that Euler's number e, of x, plus 2. But I'm going to tell you, no mathematician ever writes that. We never write the logarithm base e. Instead, we just abbreviate it as ln, or natural logarithm. E is no different than any other base 2, base 5, base e, doesn't matter. Right? It still works as a base. And so the graph's going to follow the same principles. This one is going to reflect across the x-axis and then go up 2. So, thinking about my vertical asymptote, right, which was the y-axis, when the graph flips, the vertical asymptote stays on the y-axis. And shifting up 2 doesn't change that vertical line either. So I think x equals 0 is going to continue to be the vertical asymptote. As far as the x-intercept, it was over here at 1, 0. We've got to move it up 2. So it's going to go there. And now I just have to think about the logarithm function flipped upside down, right? Reflected. So instead of going down along the vertical asymptote, it's going to come up along the vertical asymptote. And it's going to slowly go down that way. Right? So just the upside down logarithm graph. All right, as far as the domain, this graph, we can see that nothing happens to the left of 0, right? The x values start just after 0 and go to infinity. And y is going down to negative infinity and up to positive infinity. right. I think that would be a good place to stop. We've kind of talked about the graphs, what a logarithm is, what the graphs look like. We'll stop this video here and we'll continue this section in the next one.